Good day guys, let's look at another problem for moment of inertia for math M6. So we'll go through the A part again and pick out everything that is important in this story. So it says sketch the graph of y equal to e to the power x. Show the area bounded by the graph, the x-axis, and the lines x equal to -1 and x equal to 1. Then show the strip that you will use to calculate the volume generated when this area rotates about the x-axis. So from my own perspective, those are the important things in that story. So I'll start by capturing every important thing down before I can start sketching the graph. So we have been given the graph of y equal to e to the power x. We have been told about the x-axis. X-axis is a graph whose equation is y equal to 0. We have been told about the lines x equal to -1 and the line x equal to 1. So it means, looking at what you see on the board, we've got 4 graphs. So whatever you are shading and putting your strip must be within 4 graphs. Then finally, the rotation. This is very important. X-axis rotation always tells me how the formula for my volume will start. How that formula ends depends on the strip you put in your diagram. So that is it. Before we go to sketching the graph, I want us to talk a little bit about what I see. I see 4 graphs. Each time I'm doing 4 graphs, 2 of them must be my limit of integration. And I read them from the same axis. You see, the best option for the limit is here, x equal to -1 to x equal to 1. I can't use them because even if this is 0, that is a graph. So these are my limits of integration. So if I understand this, I can already say I know my limit. And each time you read your limit from the x-axis, that tells you where your strip in your diagram goes. So I'm already having an idea of the kind of strip I will need here, because if my limits are from the x-axis, if my x-axis is horizontal, the only strip that can go there is a vertical strip. So that is the information I've already picked out just by studying those important items. So it's now time to look at our graph. So for our graph, my limits, one is in the second quadrant, one is negative, one is positive. So that shows that I need both the negative and positive side of the x-axis. So that's my x, that's my y. So if I want the graph x equal to -1, I just choose where I want it to be on the x-axis. So I put my negative to be on the left side of 0. So that's my x equal to -1. Then for x equal to 1, it should be on the right side of 0. So I choose where I'll get my 1. I hope I got it right. I'm just trying to make sure the distance from 0 is approximately the same. So this is my x equal to 1, and this one is my x equal to -1. Then once I put the x-axis, it means I'm done with the graph y equal to 0. So you see I've sketched 3 graphs already. So what is left is the graph of x equal to e. So usually such a graph should either come this way or the other way. If you are that kind of student who is not so sure which way to go, this is how simple you can help yourself. So the first thing is you check where does the graph touch the y-axis. So if I want to know where the graph touches the y-axis, I go into that equation and make x 0. If I make x 0, I'll see e to the power 0, which is 1. So I can choose where I want to put my 1, so I know the graph will touch the y-axis here. Then I can now use the limit to guide me. The limit, what I'm trying to do is just to plot them, put them there to see whether the numbers I'm getting, are they bigger than 1? If they're bigger than 1, then I go up. If they're less than, I go down. For example, if I substitute 1 there, I get e to the power 1. From your calculator, you should be seeing that e to the power 1 is approximately 2,7. So it means when you're at 1, you should be around 2,7. So if this is your 1, this is maybe your 2, that is your 3. So you see that when you're at 1, you're around 2,7. So your graph should touch there and go there. So you see, you already have an idea of the shape. If you try the same thing with -1, If you put -1, we'll get e to the power -1. Check from your calculator what is e to the power -1. This is for those who don't really have an idea of the shape. You see that it's 0.36. 0.36 is a number below 1. So 0.36 tells you that if you're at -1, you should be somewhere there. 0.36 should be somewhere there at -1. So it gives me a full idea of how the shape should look like. So that way I can put my sketch like this. So here we have succeeded to get the correct sketch. We must remember that the exponential graph does not touch the x-axis. So now it's time to shape the portion surrounded by 1, 2, 3, and 4. So the exponential is there, x equal to 1, x equal to -1, x-axis. So I'm shading that portion under the exponential graph. So that is the portion under the exponential graph that I have shaded. I've indicated the portion surrounded by the 4 given graphs. So now it's time to put a strip in the shaded portion. So your limit, as I keep telling you, it should guide you. If your limits are right from the x-axis, your strip must touch the x-axis. The only strip that can touch x is a vertical. You see, a horizontal will never touch x. And a horizontal is eliminated because it's touching more than it's changing graphs. You see, a strip must touch the same 2 graphs all the times. If you go down there, 1 graph has changed. So the horizontal is eliminated, but vertical strip will keep on touching the same 2 graphs. So with my vertical strip, I put it anywhere I want in the shaded portion, since I'll keep on touching the same 2 graphs. That strip touches the x-axis, telling you that all your formulas in this equation must end with dx, and even your limit you read from the x-axis. Another information from the vertical strip is that all your graphs must be labeled using y. The 2 graphs, that the strip is touching must be labeled using y. The first graph will pass above the strip, which is y1, which is e to the power x. That's the graph that passes above the strip. You see, it's the exponential graph. Then the graph below the strip is the second graph. So my second graph is a 0. So with that, I'm done with my graphs. It's now time to calculate the volume. So to calculate the volume, rotation is where I start. My rotation tells me how my formula starts. So my rotation is Vx. My strip on my diagram tells me how it ends. If my strip touches the x-axis, then my formula ends with dx. So I go to my formula sheet, page number 5. For n6, you get pi integral from a to b, y1 squared minus y2 squared dx. So that is what I get. Then I start substituting into the formula. A and b, you will see from where you started shading to where you ended on your x-axis, because your formula ends with dx. That is, if you didn't already pick it from there. So you get from -1 to 1. y1 squared means I'm squaring that. To square exponential means you multiply it by itself. And if you're multiplying 2 numbers with the same base, you add the exponent. So y1 squared is simply e to the power 2x. y2, you can see it's a 0, making life easy for us. Then we integrate. If you integrate exponential, you get e to the power 2x over 2 from -1 to 1. Then you substitute your limit, you get e to the power 2. If you put 1 over 2, then minus, you repeat the process, you get e to the power -2 over 2. Then you can go to the calculator to check what is happening. So in the calculator, if I look at my story, I see that pi and e, let's say pi is common, so I will simply take my e to the power 2, 2, then minus e again to the power -2, and 2, that's what I'll put in my calculator. Whatever answer I get, I multiply it by pi. So my answer is 11,394. So that's my volume. I get 11,394 unit cube. So that's how simple it is to get my volume. So I guess that is okay for everyone. Now let's go to the C part, which says we should calculate our moment of inertia. So moment of inertia, my starting point is to check my rotation also. My rotation remains x-axis rotation. So it tells me that my formula for moment of inertia is Ix. As an N6 student, you start from page 6 of your formula sheet to copy the general formula for moment of inertia, which is r squared dm, and that continues as density, the integral from a to b of r squared dv. So that is our general formula for moment of inertia. So our job now is to develop this formula with the help of our graph and that one, which generally will replace dv, an element of volume, by the formula for our volume. But before doing that, it's always important to check what kind of formula is this. Is it disk or shell? So if I check, if my formula starts with pi, that's the disk method. As you can also see, another way of knowing the disk method is from your graph. You see that your strip was vertical, perpendicular to the axis of rotation. That's the disk method. So if you have the disk method, then your formula is developed already for you. You simply go to circular lamina on page 6 of your formula sheet. You will see the formula for Ix, which is the integral from a to b of y to the power 4 dx. So all you need to do is to adjust the y there to accommodate y1 and y2 on your graph. So I'll just say y1 to the power 4 minus y2 to the power 4, which will still reduce to y to the power 4 because you can see from our graph that y2 is a 0. So that is how simple it is. Then I start substituting. So if I'm substituting, a and b are the same, negative 1 to 1, y to the power 4, our y1 is e to the power x. So if I want e to the power 4, e to the power x, all that to the power 4, you just multiply that, you get e to the power 4x, or you can just say e to the power x 4 times, you still get e to the power 4x. So we get e to the power 4x, or y2 is 0, so that's what we get. Then now integrate, we'll get e to the power 4x over 4, negative 1 to 1. Then we'll substitute our limit, we'll get e to the power 4 over 4. That's my upper limit minus the lower limit, which is e to the power negative 4 over 4. Then we go to the calculator to see what is our moment of inertia. So in my calculator, I will simply be taking e to the power 4 over 4 minus e to the power negative 4 over 4, since pi density over 2 is common, or I can still see that 4 is common. Then I just take e to the power 4 minus e to the power negative 4, then I divide by 8, since I have 2 times 4 being common. So I can say pi density over 8 is common. So that way you can make things fast. So I'll take e to the power 4 minus e again to the power negative 4. So that gives me 54,579. Then I divide by 8. You see that is 2 times 4. I will divide by 8. Then I multiply by pi. You see there is pi there. So I get my 21,434. So I get 21,434 times density. So that's my moment of inertia. So we can now move to the last part, the D part, which says we need our answer. Express your answer in C above in terms of the mass. So to express your answer in C above, C was calculating moment of inertia. What usually guides us is the relationship between mass, density, and volume. So for N6 students, you see that relationship on page 5 of your formula sheet, which tells you that your density is mass over volume. And that reminds me that to write this answer in terms of the mass, density should be replaced by mass over volume, reminding us that we are dividing by the volume, then multiply by the mass. So what I will simply do is that I will copy that moment of inertia, which is 21,434. Yeah, that's what supposed to be 433. So I didn't capture it in the calculator. Well, it's 433. Then what do? I divide this answer for my volume. My volume was 11,394. 11,394. Then I multiply this by mass. So that is how simple it is. So I will divide by 11,394. 394. It gives me 1,881 m. So guys, that is how we calculate our moment of inertia and then write our answer.